Welcome to myprojectbazaar.com. Our product title is a 3-base inverter for a standalone distributed generator system, adaptive voltage control design and stability analysis. Let us see about in this proposed implementation is a robust adaptive voltage control of 3-base voltage source inverter for a distributed generation system in a standalone operation. First, the state space module of the load side inverter, which considers the uncertainties of the system performance and also that parameters, is established. The proposed adaptive voltage control technique combines an adaptive voltage control term and a state feedback control term. The former compensates for system uncertainties, while the latter forces the error dynamics to coverage to zero. In addition, the proposed algorithm is easy to implement, but it is very robust to system uncertainties and certain load disturbance. In this implementation, a stability analysis is also carried out to show the robustness of the closed loop control system. The proposed control strategies guarantees excellent voltage regulation performance, that is fast transient response, zero steady state error and low THD under various type of loads such as balanced load and nonlinear load, and also corresponding output is compared with the PI controller output. This implementation is done in MATLAB simulating environment. Next we see about flow diagram of our product. In this proposed flow diagram, the input source is a PV module. The PV module is nothing but it having the solar array panel. The solar array consists of number of solar cells is connected in series or parallel. In this proposed implementation, the solar cells are connected in series, and also in each array consists of 6 solar cells. Totally 12 solar arrays are connected, and the panel consists totally 72 solar cells, and also the output of the solar panel is 44 volt, and also this PV module is getting from the solar energy from the solar irradiance. Mainly the solar panel is works on as a solar energy is converted into electrical energy in the form of DC, and also that PV module output is fed into DC to DC boost converter, that is a DC to DC conversion block. In that block, the PV module output voltage will be further boosted into some value, and also next that output of DC to DC boost converter is fed into DC to AC conversion block. In that block, the process is DC to AC conversion, that means is electrical energy is converted into one form of energy into another form of energy using of power electronic switching devices, and also those power electronic switching devices is controlled by or triggered by using of space vector pulse width modulation based PWM controller. And finally the output of DC to AC conversion is fed into the load and through a LC filter. The load is considered nonlinear if its impedance changes with the applied voltage. The changing impedance means that the current drawn by the nonlinear load will not be sinusoidal. Even when it is connected to a sinusoidal voltage, these non-sinusoidal currents contains harmonic currents that interact with the impedance of the power distribution system to create voltage distribution that can affect both the distribution system equipment and also the load connected to it. In the past, nonlinear loads were primarily found in heavy industrial applications such as arc furnaces, large variable frequency drives, heavy rectifiers for electrolyte refining. The harmonics they generate were typically localized and often addressed by knowledgeable experts. Typical linear or nonlinear current waveforms are good. Next we see about running process of our product. In this proposed implementation is done in MATLAB simulating environment. First open the MATLAB main window and create a new model file. After creating that, we arranging the elements as per the circuit diagram is given in the base paper. From the MATLAB Simulink Library Browser. In the MATLAB Simulink Library Browser, we using two major blocks. One is the sim power system block, another one commonly used block. From that blocks we getting the elements, and after that we arranging the elements as per the circuit diagram in the model file. After arranging that, we click the run symbol icon, then the output will be shown in the corresponding scopes. First one is the IV curve. This curve is drawn between current and voltage in the solar panel, and next one is the PV curve. This curve is drawn between power and voltage in the PV panel, and next one is the input source voltage, that is the 260 volt, and next one is the input voltage waveforms, and this is the corresponding output scopes for balance load. This is the output AC waveform, and this is the output AC current waveform, and this is the staircase waveform. Before that, the inverter output is always staircase, and next one is the unbalanced voltage and current waveform using unbalanced loads. So this is the input output voltage waveform, this is the current waveform. The output voltage around the 250 volt, and the output current around 3 amps. And next one is the non-linear load waveforms. So here we can see the waveform of non-linear output current waveform is not a sine waveform, and also this is the output voltage waveform. The voltage is also around 250 volt. So using of non-linear node, the output sinusoidal is current is not obtained, and also this affect the harmonics and also inject the harmonic current, and due to this kind of waveform we implement the statcom or other shunt active filters for recover this current waveform into sinusoidal. Thank you for watching this video.